Okay, this is a re-recording of class from September 7th, last Tuesday, the fourth and final day of the Matlab tutorial, since most of that class meeting turned out to not be recorded. So I'm just going to step through the Matlab commands that I executed on that day and get this recording into Canvas so you can all um, have a record of everything I was done that day. Okay, my diary going. All right, so this is the last part of the Matlab tutorial. I'm going to begin with showing some basic graphics commands. So first, I'm going to create a vector of equally spaced points in the interval -1 to 1. So I'll just use a spacing of 1/1000th. I could also create this vector using linspace. I just tend to prefer doing it this way. So what I want to do is plot function y equals x squared. So I'm going to be plotting y versus x. So to get my y values, it's tempting to simply do this since we know that the up arrow is used for exponentiation. But what we find is that when we do it this way, because x is a column vector, I notice the transpose here because this expression is a row vector. I transpose it to make a column vector. Again, that's a personal preference thing. But that's not something that I can exponentiate in the usual way. So squaring using this syntax is for square matrices. And also the power itself should be a scalar, which it is in this case. Otherwise, I should use dot up arrow. So like this, y is x dot squared. This is for component-wise exponentiation. So there are certain operations for which the dot form is required. For example, suppose you have two matrices of the same size, you can use dot star to perform entry-wise multiplication, as opposed to conventional matrix multiplication that requires the number of columns in the first matrix equal the number of rows in the second. But operations such as addition and subtraction do not need any dot form because those operations act in a entry-wise manner anyway. So now that I have my vector of y values, I will go ahead and plot y versus x, and we see the familiar parabola, y equals x squared. Now, it's important to have proper annotation of your plots. For instance, labeling the axes. So I'm going to make this a little bigger. Okay. So I can do x label the x-axis with whatever text, and then the same for the y-axis. And you can see we have the x-axis label here and the y-axis label here. Notice the text for the y-axis label is rotated 90 degrees, so it aligns with the axis. I should mention that commands such as x label and y label that annotate with text are equipped with a very limited LaTeX interpreter. So if you want to use basic LaTeX commands such as including Greek letters or subscripts or superscripts, then you can do that. But again, it's limited. All right. Now, let's plot something else. I'm going to plot the function y equals x, but with a different appearance. So this third argument, the optional third argument, indicates color and style. So the R means plot in red. The default is blue, as you saw with the parabola. And then here the double dash means plot a dash line. So MATLAB doesn't actually plot curves. What it does is, depending on how plot is called, it will connect the dots. So whatever data points you are plotting, by default, MATLAB will connect them with line segments. It's just that if you have a large number of points with little spacing between them, those line segments can together create the appearance of a smooth curve, as we saw with a parabola. Okay, so now I go ahead and plot y equals x, and let's take a look. And we see that the parabola is gone. So plotting commands by default will wipe out whatever was in the figure window before. This is contrast with, for example, Python, where the default is to superimpose curves. So if you don't, if you want that superimposing, then you need to use what's called the hold command. So if I do hold on, so the hold command, the hold on says keep whatever's there in the figure window, and subsequent plots will be superimposed on it. Or you can do hold off to turn that off. Hold by itself toggles the hold state, which by default is off. I always use hold on or hold off just so I don't have to try to keep track of what the hold state is. So now I'll plot something else. I'll plot the function cosine x, and I'll use K for black because B is used for blue. And the O indicates that each data point will be plotted as a circle, so they will not be connected. So we have that here. Now, what it looks like a thick black curve, but what it really is a large number of circles very close together. So because there's so many of them so close, it creates the appearance of this thick black smooth curve. So what I'm going to do is, okay, since I don't want this, I can actually delete it without disturbing anything else. So if I click on this arrow here, that I can use that to, I can now select parts of this plot. So I can select this right here, or I can select this. This is what I want to select, and now I can just hit the delete key, and it's gone. And then I can get out of selection mode by clicking the arrow again. So now I'm going to make a vector of x values, another vector of x values, with less spacing, so I have fewer points, still from -1 to 1. And I'll plot cosine of that. The black circle is not connected. And now you can see what I mean. That is plotting the individual data points. Now I can also more annotation. I've shown you how to label the x and y axes. I can also put a title on the graph. So a title command with whatever text places a title at the top. So we see that here, playing with plot. I can also add a legend. So the legend command can be used to label whatever curves you have. This is good for including plots in papers or presentations, for instance. So the first function I plotted was y equals x. So I'll label that x. You need to put the labels in the same order in which the curves were plotted. So I plotted y equals x first, and then I plotted cosine, so that'll go second. And you can see the legend here in the upper right corner. So the first curve was a red dashed line for y equals x, and then the second one was a curve of black circles for cosine. So the x and cosine are the text labels that I specified. Okay. Now, another command to add text to a plot is GText. So I give as an argument some text. So once I hit enter, what will happen is I can move my mouse pointer, and the crosshairs indicates where text will be placed. So I can move to whatever location I want, and as soon as I click the mouse button, or okay, the touchpad button in this case, that's where it'll place the text. Now, all I've shown you here are 2D plots. Matlab also does 3D plots using a plot3 command and other commands. GText can only be used for 2D plots. Okay. Now, notice here at the top it says Figure 1. I can use the Figure command to create new figure windows. So you see here, this one is called Figure 2. So by default, it'll choose the first positive integer that is not assigned to a figure and create a new figure window with that number. I could also specify a figure number. For instance, figure 10 by passing 10 as an argument. So we see here figure 10. I can also put more than one set of axes in a given figure window. So far you've seen figure windows that only have one set of axes, but to have more, I can use the subplot command. So if I do, for instance, subplot 2, 3, 1, this indicates that it needs to create a 2 by 3 matrix of axes, so 2 rows, 3 columns. And then the 1 here means make the first set of axes the active one for subsequent plotting commands. And axes are numbered on a row by row basis. So in this case, we're going to have 6 axes total. So the first row from left to right would have axes number 1, 2, 3. The second row from left to right would have axes 4, 5, and 6. So I go ahead and do that. And then when I look at figure 10, here we have the first set of axes. So now in that first set of axes, I can plot something. I'll do, for instance, plotting the exponential. And it will go to that set of axes. So now if I want to work with another set of axes, for instance, the second one, then I'll do subplot 2, 3, 2. Be sure to keep these the same or it'll mess up whatever axes were already there. So now the second one is the active one. And that's what we see here. So if I use more plotting commands, then it will go to this set of axes. Now, I'm going to show you something fun I did with Matlab several years ago. It was actually for this class, or I actually think it was the second course, Math 461, 561. So I'm going to show you the inspiration for this. Okay, right here we have stick figures doing dances that illustrate certain functions like sine, cosine, x, 1 over x, etc. So I wrote some MATLAB code that would draw figures like these that would perform dances using functions that were specified by the user. So I'll go ahead and show you that old code. So first I'm going to use the command close all to get rid of the figure windows that I have. Okay. And I'll go into that folder. Okay, so what I'm going to do is show math dances using sine and cosine. So the first argument is a cell array of curly braces are used to specify a cell array as opposed to a conventional array that's specified using square brackets. Second argument is a cell array of text labels for these functions in the same order. So I go ahead and run that, and here we see sine and cosine shown. So what I did to create these, I used, let me make this bigger. polar coordinates for the head and the lower part of the mouth and also the eyes. I used a fourth degree polynomial, a quartic, for the body, and what I would do is choose a point on each side to as a starting point for the curve. So here for sine, and here and this cosine. So it took a little trial and error to get it to work. You see the arms don't quite match up, and the reason for that is I have a body going back and forth. I'll show it again. Notice that the body is moving slightly from left to right. And the eyes are moving independently, which some students found rather creepy. Okay. But what's even creepier is if I use different functions, like tangent and the exponential. So of tangent, we have the vertical asymptotes shown here. And then with exponential, we have the left arm gets extremely long because of how rapidly the exponential function grows. I'll show one more with just one function, the absolute value. So it's just flapping his arms up and down. Okay. All right, so that's all I have for graphics. Now I'll shift gears to polynomial functions. And I'll just show selected ones here, but you can do help polyfun at the prompt to get the full list of polynomial-related functions. All right, so I'm going to close everything down, graphics-wise. Okay, so to represent polynomials in Matlab, use a row vector of the polynomial's coefficients. And very important, coefficients need to be listed from highest degree to lowest. So my standard example, polynomial x squared minus 5x plus 6, I would use this row vector, 1 minus 5, 6. So this represents this polynomial. Or this vector represents this polynomial. So now the first polynomial function I'll show you is roots. So roots takes as input a row vector assumed to represent a polynomial, and roots will find roots of that polynomial and store the result in the column vector R. So we know how to factor this polynomial. It's x minus 2 times x minus 3. So 2 and 3 of it roots, and sure enough, that's what it returns. And I can use indexing to refer to individual roots within this column vector, just like with any other array. Roots handles complex roots also. So if I form this polynomial, 1, 0, 4, so that's for a polynomial x squared plus 4, which has roots plus or minus 2i, and that's what we get here. Now, the poly function, on the other hand, takes as input a vector of roots, and its output is a row vector consisting of the coefficients of the monic polynomial that has these roots. A polynomial is monic if and only if its leading coefficient, so a coefficient of the highest power of x, is equal to 1. So So a monic polynomial with roots 3 and 2 is x squared minus 5x plus 6. So, since poly takes in roots and gives the coefficients, whereas roots takes as input the coefficients and returns as output to roots, you could think of roots and poly as, instead of being inverses of one another. Because roots go in, coefficients come out, coefficients come in, roots come out. So sure enough, I get the same values back, although not necessarily in the same order, so we can't assume that. So is roots really the inverse of poly, generally speaking? Well, let's do another example. So here we have 5 roots, 1, 2, 3, 4, 5. So poly will form a fifth degree polynomial that has those roots, and then roots will compute the roots of that polynomial. So we should get the numbers 1 to 5 back. Let's see what happens. Well, a little bit off. So here we do have a number very close to 5. This number is very close to 4. This is very close to 3, 2, 1. So we do get 1, 2, 3, 4, 5 back, except for some round off error on the order of, let's see, 1, 2, 3, 4. So around 10 to the minus 13 is the magnitude of the error in this case. So now let's take things further. So we could say, yeah, yes, we are inverses of each other, but what if we try something of higher degree? So 1 to 20. And you can recognize numbers close to 20, 19, 18, all the way down to 1, but the error is much greater than in the previous example. Here, this is supposed to be 15, and it's 0.05 away from that, roughly. And if I live in further, say 1 to 50, the error is so bad that we get complex roots. So roots, Polyant roots fail very badly in this case. Although this actually makes sense if you examine the coefficients. So polynomial has roots 1 to 50. If I look at its coefficients, I'll use a column vector. It's easier to see. So these coefficients for okay, remember poly orders coefficients from highest degree to low. So here the highest degree coefficients, it seems like they're 0, but look how large these numbers are, on the order of 10 to the 65. So these coefficients cannot even be represented accurately, because you can only expect 15 or 16 decimal places to be represented accurately. So there's many decimal places that are lost. So this is not really an accurate representation of a polynomial that has roots 1 to 50. So with that in mind, it should not be a surprise that we don't get those roots back when we apply roots to this polynomial. The case of 1 to 20 is called Wilkinson's example. And so Wilkinson is a very influential numerical analysis from back in the 60s. There are a lot of things named after him. He had an excellent book on the algebraic eigenvalue problem that I highly recommend. And this example of his was meant to highlight the difficulty of computing polynomial roots, how it's a numerically unstable problem. So especially once you get to high degree, we really can't expect great accuracy, unfortunately. How roots works is it computes a matrix called a companion matrix, whose characteristic polynomial is a polynomial you want the roots of. And then since the roots of a characteristic polynomial are the eigenvalues of a matrix, roots then uses standard eigenvalue methods to compute the eigenvalues of that companion matrix. And it really is numerically the most effective way to compute roots. It's just that for polynomials like these, if a problem is so badly conditioned, conditioning is something I'll discuss in section 2.1, that there's really no hope of solving a problem accurately in this case. Okay. The next function related to polynomials, for evaluating a polynomial, called Polyval. So I'll make a polynomial for x squared. So if I do Polyval p, so first you specify polynomial you want to evaluate, and then you specify the x values to be substituted into that polynomial. So I'll just use the column vector 1, 2, 3, 4, and sure enough, we get their squares. Okay. Here's some calculus operations on polynomials. So I'll go back to my favorite example. Okay. First, for derivative, I do Polydur. So a derivative of x squared minus 5x plus 6 is 2x minus 5. So polynomial coefficients come in, polynomial coefficients come out. Just using the power rule for differentiation. Also, the antiderivative, that's Polyint. And I'll apply it to the answer that we got here, 2x minus 5. So we take the antiderivative of that, but we're not going to get this back because, as you know, the antiderivative is not unique. So the antiderivative of 2x minus 5 is x squared minus 5x plus an arbitrary constant. By default, Polyint will set the constant of integration to be 0. Now, if you look at the help page for Polyint, you'll see that you can specify a different constant of integration if you want. So most of the polynomial functions we've seen have a prefix poly, except for roots. Here's another one that does not. For polynomial multiplication, now use an example for which the answer can easily be figured out in your head. So first I have a polynomial for x minus 5, and then x plus 5. So you know that the product of these two is x squared minus 25. The way you multiply polynomials like these is to use a function called conv. Conv is short for convolution. And sure enough, we get x squared minus 25. So conv takes two vectors and takes very convolution. So that's useful in many areas of mathematics, such as, for example, partial differential equations, signal processing, etc. But the process of convolution happens to be mathematically equivalent to that of obtaining the coefficients of a product of two polynomials. So there's a function that serves more than one purpose. Now, what about other polynomial arithmetic, like addition of polynomials? You have to be careful. So if I were to add these two, we know what the result should be 2x. So if I go ahead and do that, and sure enough, that's what we get. But if I change p to my favorite example again, and then I do p plus q, well, while it's fine to add these polynomials, it's not fine to add these two vectors p and q, because the same the standard rules of matrix addition apply. They must be the same size, but P is a row vector of length 3, Q is a row vector of length 2. So what you need to do is pad the polynomial of lower degree with zeros to the left. So if I do this, then the two polynomials are added, and we get x squared minus 5x plus x, so minus 4x, and then plus 6 plus 5, so we get the constant term of 11. So in general, that if the length of P is greater or equal to the length of Q, then you can do the following. P plus, and you need to include the right number of zeros here. So zeros, a row vector, and it'd be the length of P minus the length of Q. Button followed by Q. So if you know that this is the case, then you can add this way. Otherwise, you would just reverse the roles of P and Q. All right. So that's all I have to say about polynomials. Now I'll move on to number formatting. So if I set x equal to pi, so pi is a special variable in Matlab that holds the value of pi to the precision possible. And here we're using format long that has 15 decimal places. On the other hand, if I do format short, which is usually the default, and I display x, then it uses only 4 decimal places. Here's another format for you, format rat for rational. So if I display pi again, we get this fraction, 355 over 113, which is a well-known fraction for approximating pi. So when displaying numbers using this format, Matlab will try to find a fraction that approximates a given number to a specified tolerance. Now, how accurate is this? Well, if I do this fraction minus pi, because I'm in format rat, it will give me a fraction, but that's not very informative. So I'm going to go back to format short and do 355 over 113 minus pi and see what the accuracy is. So it is for a relatively simple fraction, that's a fairly accurate approximation of pi with error on the order of 10 to the minus 7. Now, if I go back to format rat, if I do 1 dot divide 2 through 5. So here I'm dividing by a row vector. Therefore, I need the dot divide. Otherwise, I would get an error. In a case like this, where we have a scalar divided by a vector, Matlab will automatically change this scalar to a vector or array of the appropriate size so that the operation can be performed. Sure enough, we get 1/2, 1/3, 1/4, 1/5. Some more formats. This one is for when you add on an E to format short or format long, it will use scientific notation. So I'll make up a number here. And we see scientific notation used here. There's also a format bank that just uses 2 decimal places. Exactly 2 for dollars and cents. And here's another format hex. Now this one's quite odd. This may not make sense now, but when I get to section 2.2 on computer arithmetic, then I will explain what this format means. But what we're seeing is how the number is stored internally using the IEEE double precision floating point standard. Okay, that's all I have for formats. Moving on to what are called function handles and anonymous functions. We've seen functions that you can write yourself in function M files, but in some cases you want to work with a certain function, perhaps a very simple one, without going to the trouble of writing it in an M file. Maybe it's a function that will be one line long, and for that you can create anonymous functions that don't have a name. They're stored in a variable. So as an example, function e exponential of sine 2x. So my syntax here, f is my variable that will hold the function handle. This syntax indicates I'm creating a function of x. So x is the input. And after that, I put the formula for the function. And this is how f is described, a function handle that has this value. So now I can substitute the argument in for x. So like f of 0, oops, I forgot to change from format hex. Okay, so the value is 1. So yes, this is the hex representation of 1. I'll just make some random values and substitute them into the function. So in this case, I could pass a scalar, vector, or matrix, and it will evaluate the function at each entry of that array. Now, you can also make functions with more than one argument. For example, I'll make a function of 2 variables. Sorry, just making sure I'm still recording. After last time, you never know. Okay. So this function will be square root of x squared plus y squared. So now I can call this function. First argument is assumed to be x. The second argument is assumed to be y. So I get the square root of 5. But now I'm going to make x and y equal to vectors, column vectors of the same length. Now if I do f of x, y, it doesn't like that because I can't use just an up arrow by itself to square a vector. So instead I need to use dot squared. So I can redefine my function. So now I can say that the function is vectorized. So I can pass in a scalar, a vector, a matrix, an array of any dimension, and it will do what is intended. It will square each entry, each element of the array, add them, and take a square root. The square root function is already vectorized, but exponentiation with just the up arrow is not. That's why I need to use the dot up arrow. So now I could do f of x, y, and it will carry it out. Okay. Now I'll show you other convenient functions. I'll create a random matrix to illustrate. The size function returns the size of an array as a row vector. By default, arrays are two-dimensional, including vectors, because they just have one of their dimensions equal to 1. depending on whether it's a row or column vector. So that's referred to as a singleton dimension. So this command here tells us that A has 3 rows and 2 columns. Size returns a row vector of the dimensions of the array that you give it. So now if I make a column vector and do size of x, still returns a row vector, 3 rows, 1 column. Now the length function, if I give a vector as an argument, it'll simply give a length of that vector. Whether it's a row or column vector, it'll give the appropriate result. What if I do length of a matrix? So A, and I created a little while ago, is a 3 by 2 matrix. It gives me 3. You can think of it as returning of a maximum of the size of A, or the largest dimension. So in this case, for a 3 by 2 matrix, that would be 3. If I did the length of A transpose, so that's a 2 by 3 matrix, again, it's going to be 3 because that's the largest dimension. Just for to use these functions intuitively, what I recommend is size for matrices, length for vectors. If what you're dealing with, if you know it's a vector, row or column vector, then length will be just fine. All right. Now another convenient function. The total number of elements in any array, num_L. So A is a 3 by 2 matrix, so total number of elements in it would be 6. Sometimes you need to reshape an array. You have something that's a matrix and you want to make it into a vector, or vice versa. In fact, I find myself doing that often, like in my research. And for that, you can use the reshape function. So A is a 3 by 2 matrix, so I could do this, reshape A into a 6 by 1 vector. So that would be a column vector. Now, a particularly convenient way to reshape a matrix into a vector, you can actually specify use empty paired square brackets. So this would have the same effect. So this is helpful in that you don't have to do something like num_L of A. So all you're saying here is you don't care what kind of matrix A is. You just want it reshaped into a column vector. So with reshape, the total number of elements cannot change. For example, you cannot use reshape to reshape a 40 by 40 matrix into a 100 element vector. It would have to be reshaped into a 1600 element vector. If I want to reshape A into a row vector, same idea. So I specify it has 1 row and then however many columns are needed to accommodate all of the entries. Now, if I bring back A, and then also it's reshaping into a column vector, notice that it begins with a first column of A and then the second column of A. So when you're reshaping, Matlab reshape is going to go through whatever entity you're reshaping column by column. So another way of putting it is reshape uses what's called column major order. That's the same order as in Fortran, which makes sense because MATLAB's lowest level code is written in Fortran because that's most efficient. C and C++, on the other hand, use row major order. Now, Python allows reshaping using either order, whereas when I checked the help page for Reshape, Matlab's Reshape does not offer that same kind of flexibility, unfortunately. Okay. Other convening functions. Sum and prod. So if I make bring back my vector v from before. So for a vector, sum and prod are very straightforward. Sum will just add up all the elements of a vector. Whereas prod will multiply all the elements together. So one thing I want to mention from what I did in class on Tuesday. Sorry, I need to go to the textbook. What I've covered here is almost everything in the Matlab tutorial. It's not absolutely everything. So what I have left out here is just a couple of items: saving and loading data. So I want to point these out in the textbook. So, for example, if you look here, I have a number of variables from my various activities. So I'm going to, I need to go back to the tutorial folder. If I use the save command, what this does is it creates a file called mydata.mat. So the .mat extension is added automatically. It'll take all these variables, their names and their values, and save them into that file. And you can see that file there now. So now what I can do is if I were to use a clear command, clear will wipe out all the variables in your workspace. So please use this command very cautiously. I'm only using it now because I've already saved everything. So clear wipes everything out. And now if I do load my data, it's all back. So here we see the simplest usage of save and load commands. It's also possible, like if I had saved, if I had listed individual variables after the file name and the save command, it would only save those variables. So both save and load can be used to apply to just a certain variable selectively. Okay. So this file cannot be understood by a text editor. This is in binary format. There is an option for save and load -ASCII to save and load text files, but it's a lot less flexible than saving in this binary format. For instance, you lose the ability to save variable names. So it's not as useful as you might like. But certainly you can look at the help pages for save and load for more information on how to use those commands. And finally, to measure efficiency, Matlab offers these commands tick and talk. So here I have an example where I use a tick command that starts the clock, and then I perform whatever operation I want, in this case, matrix multiplication, and then talk will stop the clock, and by default, it will print out how much time the operation took. Notice it's not always the same because of the operating system overhead, etc. But you can also take a result of talk and save it into a variable, so then it won't print, but at least you can store that time in a variable. Now, measuring performance with Matlab is not always the best idea because Matlab uses a combination of compiled and interpreted code. I've actually modified computations so that the number of arithmetic operations performed is greater, but the time is less. And that's because of what operations are being performed. For example, matrix multiplication is particularly efficient because it's using low-level Fortran code, but using code from M files is interpreted, and that's going to be a lot slower. So that's something to keep in mind. That comparisons of performance in MATLAB should be taken with a grain of salt. But what the information from Tick and Talk can be used to make your code more efficient. There's also this command, run in time. So you can use that to run some code of yours, and then it will give a breakdown of how much time was spent in various functions that were called. And I found that very helpful in my research to find hotspots where a lot of time is being taken so I can focus on making those parts more efficient. And so that's the best use of my time in terms of making the code more efficient. Okay, so that's the conclusion of this MATLAB tutorial. So I will get this posted in Canvas under September 7th, since that's the class where this last part of the tutorial was supposed to happen. Okay. Well, it did happen, it just wasn't recorded properly until now.